I was raking up leaves on the lawn last night and I got a good picture of Sky. She's so cute. The fall colors are nice, huh? Today we will finish chapter 5. I feel pretty confident. And we'll start chapter 6, the SN2 reaction. Yeah, Sky saw a dog across the street. Or just anything. She's always on the lookout. So tutors are needed for next spring. We're always the tutoring center is always looking for tutors, and the organic chem students are great because they've already had general chem and probably a lot of math and other classes. So if you've thought about tutoring before, you should try it. Being a tutor, it helps you build your foundation on the stuff you've already been through and get stronger at it, so you have a better foundation. But it also teaches you how to like learn, because you have to explain things to people in multiple ways, and while you're doing that, you get good at that. And then when you have to teach yourself something, you get good at trying to look at it from different ways. So I would suggest, if you can, try to become a tutor, and they pay decent, I think. And but if you want to do that, ask me and I can give you like the recommendation. I can fill out the recommendation form for you. Okay, tough love time. So I want us to do well. I need us to do well. And so I want to help make sure you guys stay on track. So I've entered some zeros in old assignments on Canvas. So things from like, homework A that was due like September, middle of September or something. If I don't have an assignment for that was ever turned into me, then it has no grade in it. And until I enter a 0, the percent total for you in the course doesn't consider that as a 0. So I went through this last weekend and I was like, okay, there was like, okay, 3 people didn't turn in homework B. So I put zeros in for it. And then other people didn't turn in this assignment. So when I do that, some people are like, wait, why did my average go down 5%? Because they don't understand that, the things they don't turn in are worth 0 points, but they just aren't calculated in until I go back and physically do that. So I want you to go through the grade book and look for errors maybe, or things if you feel like, oh, wait, I did turn that in. And then sometimes it will be that you did try to turn it in, but it like got messed up in an upload or something. And I'm understanding of that. If that's the case, you can tell me about it and turn it in and I won't count it late. So check that out. And it's not smart to take the after exam quiz before you've done the exam correction. So a number of students this week came into lab and they took the after exam quiz. Some of them did poorly on it. And then I looked and saw they didn't even do the exam corrections. Some actually did do the exam corrections afterwards, still did good on the after exam quiz. So they were bucking the trend. But yeah, try not to do that. You got to really keep on top of this stuff because I want you to learn this stuff. And a few of you still don't know the radical halogenation of an alkane mechanism to the point where it's in your head memorized. And I've tried to say that lots of times, just memorize that, write it out a bunch. And those of you who didn't know that mechanism well on the exam, like the first question that just says do the mechanism, you didn't do well on. And then there was like 4 more questions that were basically you have to know the mechanism. So it just killed your exam score. And then when you came into the quiz, you might still not know it after exam quiz, and it's just not looking good. So you have to like memorize these reactions. That's the best way to do this class. And each mechanism you memorize, you get better at them. So they become easier and easier to learn. So yeah, get going. You got to really start practicing. And have you worked through Monday's lecture material yet? So if you haven't, taken a moment to go through all the sample problems we did in that lecture and tried them on your own and then made up your own, it might hurt you for exam 3. So check that out. And have you started the homework D, chapter 5, Stereochem stuff? If not, it might be a bad sign you're behind, because we'll finish chapter 5 most likely today, and that's going to be due. I'll set the due date after today's lecture. And the Stereochem workshop, that's due today and tomorrow. So if you haven't finished that, then you're behind. Let's go. Tough love. Let's get going. The exam's in a couple weeks, I think. And your performance on that exam is more dependent on today than in 2 weeks from today. It's what you do today that matters. So let's get going. All right, so finish the wet chem of chem. I think everybody finished crystallization lab, all the people that were here when I polled the class. So that's good. Get that report in this week. And then the chromatography lab assignment, it's not in progress. Wait, I got to change that. It's done. I finished that this morning, finally. So the chromatography lab's ready to go. It was already enough ready to go to have you prepare for this week. So read up to the point of Webcam by today and tomorrow. This way you can, when you get to the point where you want to do that lab, you don't have to like go, oh, I'm ready for that lab now. Let me go read the intro. I'm in lab. Let me do the chemistry. And I've mentioned before, I'm going to stop filling in that due dates sheet because it's just like another thing I had to do. So just keep track of, how things are. Try not to make them late. Try to turn them in on time. But if you're late, make them under 4 days. And you can come work early as always. Here's the times. Stereochem workshops due today and tomorrow. Try to get every answer correct. So ask for help with it if you don't know how to do something. Honors students. Okay, I said this last time. I'll try to get you honors assignments in lab today and tomorrow. Yeah. And don't forget to do the extra credit. I mentioned that before. That's a good one. And if you're not doing as well as you like, come to office hours. Yesterday, I had a good turnout for office hours. I like it. It was good. So treat this, try to get more of you to come. I want more of you to come as well. So treat it like another class, come with questions or not. And if you feel behind, embarrassed to come, still come. And an hour of study with me is like maybe 4 on your own. Okay, any questions about the intro? Was my tough love too much? I went from cute sky to tough love. So today I say we should do a Fisher to a zigzag in reverse. Okay, let me show you some of this. So today we're going to do some Fisher projections some more, and then we're going to do the stereochemistry of reactions. That's a good one. Okay. So I think, oh, actually, I'm going to start looking at the schedule very first here, and then I'll do the Fishers. So I look at my schedule here. Exam 3 is week 13. What are we now? We're week 11, huh? Oh. Yep, I guess the withdrawal with the W date has passed, or has it passed? Yes. Oh, I should look at the things. So hopefully you didn't withdraw, or maybe you withdrawed from another class. You have more time for O.Chem. I hope you didn't have to do any of that. And so we have today's lecture is here, and then we have one more lecture, 3 more lectures, and it's exam 3 time. And Thursday, oh no, 4 more lectures because we have a Wednesday lecture still here. So 1, 2, 3, 4 more lectures and an exam. Material is going to keep coming, so keep on top of it. And I had a question in the chat. Annalise asked about the workshop, spectroscopy workshop. You can ask me for help tomorrow in lab, but try to finish everything, or at least start everything that you can. And then the other thing I wanted to show you this guy. I'll show you this one real quick. Slideshow. Okay, so remember, Fisher projections have the vertical lines curving away from you, and the horizontals are wedged out at you like the caterpillar trying to give you a hug, like Heinrich. Oh, come here, give me a hug. Let's have some watermelon. And then, so Heinrich's got what? 1, 2, 3, 4, 5, 6, 7, 8 arms this time. And I would like you to know, I'm going to ask you to do this on the next exam. I'm going to ask you to understand the structure of a Fisher projection and be able to change it from a Fisher projection into the zigzag form. So this is going to click us through a quick version of that, and then I'll do another one on the Jamboard. Okay, here we go. So the first thing I did is I knocked it over differently than I did in lab the other day. I knocked it over to the left. See this alcohol on top? I made that go over here to the left, and the methyl on the bottom, it went to the right. So I just kind of knocked it over. And when I did that, it should make sense that, you know, these hydrogens, these three and the bromine should be on top. And then the methyl and the alcohol, they should be on bottom when it's knocked over like that. And then the next thing I'm going to do is rotate it back like this, like the molecule has all these groups sticking out at you. And now I'm going to rotate them in such a way where they go whoop like this. This is, my fingers are representing the wedge groups. Like this could be maybe the bromine and the hydrogen. And then this one could be on the very other end, the hydrogen and methyl. I'm going like that. So hopefully you can see that if I rotate like that, the bromine is going to be dashed and the hydrogen is going to be wedged here. And if let me number the carbons real quick, so hopefully you'll see what's going on. All right. Did that work? So let's go like 1. No, it did not work. If you pick a pen color, does that mean you haven't picked the pen? No, I don't care. All right, we're going to do examples on the Jamboard. So after we get into this form, then we'll make it into the zigzag, which I don't have on this slide. And that's kind of disappointing. But let's do it on the Jamboard. Okay, so I'll make up the Fisher, say with 4 stereocenters. Let's pick an interesting one. Let's go carbohydrates. One, two, three. Oh, yeah. 1, 2, 3. Oh, yeah, these are good. Let's go glucose. D plus glucose. That'll be a good one. So that's the common sugar you learn about in biochem, C6H12O6. So I'll draw it up again as a Fisher without the atoms labeled so much. So here, let's go. The aldehyde is commonly abbreviated as CHO. Here's my first stereocenter. It's got the alcohol on the right, the hydrogen on the left. And then it's got another stereocenter, alcohol on the left, hydrogen on the right, and then the alcohol is on the right, hydrogen is on the left. And again, alcohol on the right, which makes this the D sugar, comes from D-glyceraldehyde. My lone pair's got pretty ugly there. Okay, and then lastly, I'll number this. This will really help us out here. Carbon 1, 2, 3, 4, 5, 6. Yep, it is again C6H12O6. Let me make sure. Yeah, that makes sense. So if I have 6 carbons and 12 hydrogens, that tells me I have 1 degree of unsaturation. That's the aldehyde. And the oxygens 1, 2, 3, 4, 5, 6. Yes. And then this is a carbohydrate, C6H2O6, 6 waters for 6 carbons, carbohydrate. Okay. And which way would you like me to tilt it? Do you want me to tilt it to the left initially, to the right? It doesn't really matter. Okay, I'll tilt it right. So that means I will have the OH here with the CH2. And then it's going to come across like this, and I'll have, that's carbon 6, right? And then I'll have carbon 5, 4, 3, 2, and then 1 is the aldehyde. Let's go 1, 2, 3, 4, 5. Okay, so on carbon 2, should my alcohol on carbon 2, should it be down right now or up? Down. Good. And then carbon 3, which way should its alcohol be, down or up? Good. Carbon 4, down or up? Down. Carbon 5, down or up? Down. All right, there we go, got it. Okay, so, but this Fisher projection, it's still going to have the horizontals wedged out. So I'm going to make that wedged now. So these are all wedged out. It is still, the caterpillar is laying on its side. So Heinrich over here was saying, oh, give me a hug, reaching the arms out, standing up, walking over to you. And then here it's laying on its side saying, oh, let's spoon, let's snuggle and watch Netflix and chill. Watch some TV. Okay, got it. And then now, this is the trickier part. We're going to twist this 90 degrees so that the wedges point up. We're going to twist along this axis, like here. So let me see if I can, I got to take it. Imagine I'm twisting it like so. I don't know if this will help you see it. I told myself I should learn how to draw in 3 dimensions better, like things like this, to help you learn it, but it's okay. We'll figure it out. So see, I'm twisting it that way. And when I do that, I'll get the following. That's 6, 5, 4, 3, 2, 1. So this is 1, 2, 3, 4, 5, 6. There we go. And so 2, 3, 4, 5, and 6, they all have wedge and dash pointing this way if they're tetrahedral, correct? And currently, all of them are pointing upward, huh? Kind of, pretty much up, right? All right, I'll explain why I'm pointing that out now, shortly. Okay, so back over to my carbon 2. So carbon 2 had the alcohol on the bottom and the hydrogen on top. When I rotate, is my alcohol going to be wedged or is it going to be dashed for carbon 2? So the alcohol is like, my thumb is the alcohol, it's pointing at you and it's on the bottom, hydrogen's on top. When my wedge back, oh, alcohol is wedged, hydrogen is dashed, huh? So alcohol wedged, I mean alcohol down, now it's wedged. Yep, so my alcohol is here. H right there. Okay, what about carbon 3? The alcohol is on the top for this one. When I go like this, is it going to be wedged or dashed? Yeah, dashed. It should be dashed. And it should make sense to you in a couple ways. You should be able to visualize it. That's the best thing. And also you should notice that, well, the alcohols are on opposite sides, so they still need to be on opposite sides. So I need one wedge, one dashed. Carbon 4, where's my alcohol? So carbon 4, it's going to be on the wedge too. Carbon 5. Wedgie. Again. Okay. So I'm almost there. Well, my goal is, I didn't even type that up. I want to go from the Fischer, F-I-S-C-H-E-R, to Zig Zag. So it is currently not Zig Zag. So to go zigzag, I'm going to take carbon 1. Now I'm going to go zigzag. Okay. I'm going to take carbon 1 there. I'm going to draw it this way. I think it's easy to see this way. I'll draw out the aldehyde. This is carbon 1. Carbon 2 is next. And I'll just start drawing the zigzag chain like we like one. That's carbon 2. Let me try to make this look nice. 2, 3, 4, 5, 6. Okay. 2, 3, 4, 5, 6. 6 doesn't have a stereocenter, so I'll just put its alcohol on. It doesn't need any special treatment. Carbon 2 has a wedge and a dash. 3 wedge and a dash. 4 wedge and a dash. 5 dash. There we go. I'll just leave 6 blank because it has 2 hydrogens and they don't need to be shown as stereocenter, like they don't need to be shown where they're at. Okay, so we have to make sure to put these alcohols and hydrogens on 2, 3, 4, and 5. We have to make sure we put them with the correct stereochem. So this is how I'd think of it. I say that this carbon 2 has the alcohol and the hydrogen pointing up. And now they're still pointing up, huh? So do you think that means the OH is still wedged on carbon 2? Yes. There it is. The OH is wedged at you. The H is dashed back. It looks exactly the same because they're both pointing up. But now carbon 3 got twisted around. Carbon 3 is now pointing downward. It's pointing down. So that means before carbon 3 was up, it got twisted around to point downward. So when it was up, the OH was dashed. What should the OH be now on carbon 3? It'll be dashed now to keep the correct stereochem. So it was dashed, but when we spin it around, it should be wedged now. If seeing that change, like the OH is dashed, is my thumb, and then when I spin it around, it becomes wedged. If seeing that, visualizing that in your head isn't working, then you definitely need to review the rotation practice. Let me see if I copy this, how does it paste into the Jamboard? I'll just copy that link then. That's actually part of homework 5. So if you've already done homework 5, you already started homework 5, you probably already reviewed that. So you're all good, but if you haven't, tough love here. I want you to do well. I need you all to do well because I need to have enough of you for spring semester 12B. I want to have the 3 sections I usually have. Rotation practice. All right. All right. Okay, so here we go. We got there's a new O.Chem professor for 12A in the spring, Eric, but he's teaching 12A in the spring, not 12B. All right. So now carbon 4. Sorry for the pause there. Just trying to keep everybody going good. Now carbon 4, I've got the OH and the H still up. So above on carbon 4, the OH was wedged and the hydrogen was dashed. So should they stay the same? Yes, for its OH here and dash back. Good. Carbon 5, it's switched, huh? Carbon 5 is down. So that means carbon 5's OH, which was wedged, when it flips down, it's going to be dashed. And we got it. So this molecule is the same as the original Fisher projection, but it's drawn in that zigzag form. I like these questions. It makes you practice your rotations and understanding the stereochem. Okay, and now lastly, how can we check to make sure this is correct? The way we can check to make sure it's correct is to do what? Yeah, check the RNSs, because if it's the exact same molecule, all the RNSs should be in the same. I'm going to do this one really fast to see. So this is A, B, C. This top one is R. The next one is A, B, C, S. The next one is A, B, C, R. I'm doing this fast. I hope I don't make a mistake. A, B, C, S. I'm pretty sure this is S. All right, so I got R, S, R, S. Let's see if I got the same over here. A, B, C, that's R. Is that the same? Carbon 2 still got an R? Yes. And then this one's A, B, C, that one's S. This one, is that the same? Carbon, yep. Carbon 3's got an S. Carbon 4, A, B, C, R. Carbon 4, R before, it was. Carbon 5, A, B, C, R again, I think. Let's see, A, B, C, yeah, is that R on this one? Oh no, did I do that one right? A, B, C. Oh no, it should be R here. I just calculated wrong initially. Easy to mix these up, huh? Yep, looks good. All right, so now we know how to go from, we've done a couple examples of this, going from the Fisher to the zigzag. So you know me, I won't quit there. Yeah, you know me. So what else am I gonna do? I'm gonna go zigzag to Fisher. Let's do it. So zigzag, let's start off with like something different. We'll start with a ketone maybe. I'll have the ketone over here. And then we'll add some stereocenters. Let's go. And we don't necessarily have to have bromines, I mean alcohols either. Maybe I'll put like a bromine here, alcohol here, methyl, and a chlorine. And I'll leave that in just as a methyl. All right, so how do I do this? Let me number my carbons to start. 1, 2, 3, 4, 5, 6, 7. Let me double check that. 1, 2, 3, 4, 5, 6, 7. Yeah, got 7 carbons. Most often people put the most oxidized carbon. We'll talk about oxidized carbons later, but the carbonyl on top. So I'll do that. I'll say I'll go like that, and then start numbering down the line here. This is going to be 1, 2, and then I'll have 3, 4, 5, 6, and 7 is just a methyl, huh? 3, 4, 5, 6, 7. So I got 4 stereocenters. Okay, so the key way to do this for me is to get the first one correct, and then use that as a reference. So see how carbon 3 is right here, carbon 3 is right here. I like to visualize this as maybe like think of this as like a person on a bicycle. A bike, right? Right here. Visualize a bike and then have it do a wheelie. How do you spell wheelie? Wheelie? I-E? And turn towards you. Let me explain that a little better. So imagine this is a bicycle. Got a seat, some handlebars. This is a terrible bicycle. You know what I'm saying now? Got a chain. Okay, the bicycle's going this way. But then the bicycle decides to do a wheelie, so it's like up on its wheels. And then as it's doing a wheelie, it's going across, pulls up a wheelie, and then it turns to like drive towards us. Then it turns, this is the wheelie. Turn towards us. So if it's turning towards us, then we're going to see like the front wheel and the handlebars right here, right? And the back wheel back there. Those are some terrific drawings right there. It's a very, what's it called? It's an avant-garde picture. It's surrealism. It's a cubism. I don't know what it is. It's yeah. It's up to the eye of the beholder. So anyways, so when that happens, will the bromine on this bicycle be pointing to the right or to the left? I got one right, one left. I have one more answer. Come on, you could do it. So the bromine's pointing out at you. And then when it comes up, it's going to be over here to the right. Can you visualize that? So I'm taking this, I'm grabbing that molecule there and pulling it up towards me. So that means the bromine will be on the right. And there's just an H on carbon 3. That's a secret hydrogen. Okay, so if you're having trouble seeing that, a model will help. And I haven't done carbon 4 yet, just 1 second. So carbon 3, the bromine should be on the right. And I can double check it though. How? Just do RNS, huh? So for RNS, the bromine is the higher priority. It's A. Those 2 oxygens will beat out the 1. So this is R. Is this still R? A, B, C. Yep. Looks like I did it right. Okay, for now for number 4, it's dashed back. It's on the opposite side of bromine, right? When it's zigzag. But then when it goes to be a fissure, they're all pointing towards me, huh? It's not zigzag. So you notice how bromine and the alcohol on 3 and 4 are on opposite sides, wedge dash. But on the fissure, should they still be on opposite sides or the same? The same side. Let me reiterate that. Carbon 3, bromine is on opposite. Carbon 4. Zigzag. So let's see how they're opposite to each other. Carbon 3 bromine, which is wedged. And then also notice that for these, the alcohol is pointing up. And the bromine is pointing down, right? So they're pointing different directions, like as far as up and down and also wedge and dash. All right. So, but when we do a fissure, the alcohol on carbon 4 and the bromine are pointing same direction, both pointing at us. So it went from like the alcohol's up, the bromine's down, to now they're like, if I had this on the side, you'd say they're both up. All right, so if they're both on the same direction, then they have to be on the same side. Because when you do the fissure, you're twisting around the zigzag, right? Okay, now for carbon 5. Carbon 5, the methyl it's on the same side as carbon 4's alcohol in the zigzag. So should they still be on the same side when I go to the fissure? Or should this methyl still be on the same side as the alcohol when it gets, when the thing gets twisted into a fissure? No. So carbon 5 needs the hydrogen over here and the methyl over here. It needs to be opposite of the alcohol because twisting it, okay? Okay, good. And now the methyl, it's on the same side as the chlorine in the zigzag, but when I go to the fissure, should they still be on the same side? No. So I think it's kind of easier to go from the zigzag to the fissure, actually. And no matter what, even if I'm very confident about doing this, I'm still going to check it. How am I going to check it? R and S, huh? So carbon 4 is let me see, same, oh, it's gonna have that bromine right away. Okay, so it's A, B, C, carbon 4 is R. Let me know if it seems I'm doing this wrong. I already messed up one, the last one, huh? A, B, C, R, yep. Carbon 5 is gonna be A, B, C, R as well. And carbon 6 is going to be A, B, C, R as well. All R's. R. So let's see. Is it the same on our fissure? A, B, C, R. Chlorine here. A, B, C, R. Looking good. And finally, A, B, C, R. Rawr. We got it. Cool. Yep. All right. So now we know how to do fissures well. On to our last outcome of chapter 5. Oh, these outcomes are in different orders than I presented the material, huh? I told you about the whole 2 to the n stereocenters gives you the max number of stereoisomers, and we did a bunch of practice with that, right? So this kind of problem, where I give you like a molecule with like 2, usually it's going to be 2 stereocenters, and then you try to figure out, draw all the stereoisomers, see how they relate to each other in enantiomer diastereomer. This will definitely be on your exam. It's been on every exam I've ever given at Sierra College with the Stereochem stuff. So expect that stuff, and we've been practicing a lot. And now for the Stereochem of reactions. It's pretty interesting. If you start a reaction with optically inactive or achiral, so if you're starting materials, your reactants have no chirality, they don't rotate plane polarized light, then your products will be optically inactive too, achiral. It's just a nice straightforward rule. You can't get chirality from the lack of chirality. If you start with optically active starting materials, so chiral, So things that will rotate plane porous light. You can get optically active products, but you don't always have to. For example, you can start with like something that's chiral and you can burn it in oxygen to CO2 and water. And that's not going to be chiral. So you can lose chirality, but you can't gain it from a lack of chirality in the first statement. Okay, let's look at some examples of this. I have a nice Stereochem radical halogenations. Let me see what this one is. I made a bunch of these. Yeah, let me just start this Google slide animation. And it's part of the homework, I think. I'm pretty sure it's part of the homework too. Has anybody gotten to that point in the homework? Probably not. Where you'll click through this and write out the examples. I'm just going to click through the beginning of this, and then I'll do a different example on the Jamboard. So, let me see where we're at too. Yeah, we're good. So I'm going to work through a radical halogenation the way I want you to answer this type of question on the exam. So on exam 3, I will give you a question like this. It will be a radical halogenation again, and it will involve the stereochem like these. So first, you want to draw out all the Regio Isomers. So Regio Isomers are what we did on the last exam too. We didn't worry about stereochem. We hadn't talked about it. You just put the bromine or halogen on the carbon that it will be on, and you don't draw the stereochem. You don't draw the wedges and dashes. You're just looking at the region where the reaction took place, not the three-dimensional nature of it. And then you'll use the mechanism to figure out the stereochem. The mechanism is the key. If you draw out the mechanism, understand the steric hindrance involved with that mechanism. Like if like, oh, the bromine can come in from this side or this side, and this side's more crowded, so it'll come into this side more often. It makes sense. So what stereoisomers are made? And then you'll ask yourself, what stereoisomers are made for each regioisomer, if any? And if there are enantiomers or diastereomers, and then are they made in equal amounts? And if not, can we guess which ones are made more? And then can the isomers cancel each other out, make a chiral group, or make a chiral group? So enough talk, here's an example. So for example, this one here, how many regioisomers will this molecule produce? This 2-methylbutane. Seeing some 3s, but I'm hoping for 4s. I want to see 4. I think you're mixing up. The people who are saying 3 are considering the different primaries as the same product, but they're not. So you want to look at it this way. These 2 methyls are equivalent on the isopropyl end here, or you can say isobutyl, or isopentyl, sorry. And then, so anyway, so these 2 methyls are equivalent. That's regioisomer 1, I'll call it. Then the tertiary carbon here with 1 hydrogen, that's regioisomer 2. And then we got a secondary. And then we have another primary methyl, but it's not the same as the other one, so it's a different product. So then you first draw out all the regioisomers. So you'll draw out the primary one, the secondary, the tertiary and the secondary, and then the other primary. Okay, so we got our 4 regioisomers. Then we'll ask ourselves, are any of these have stereocenters? So what did I do? Did I go backwards? Identify stereocenters. So it's interesting. The regioisomer 2 here, where I circled it in blue, that carbon currently as a reactant has no stereochemistry, right? Because it has just 2 methyls. But now it has stereochem. Because this methyl is different than that methyl. So we created a new stereocenter. When we add to the tertiary carbon, it's not a stereocenter still because it still has the 2 identical methyls. When we add to carbon 2, we created a stereocenter. And when we added carbon 1, we did not. And so what we have to do next is figure out what to do with these 2 here. So do we make both of these enantiomers? If both are they made in the same amount? So let's look. Same here. Do we make these 2 enantiomers? Both are made the same amount. So first you want to draw out the mechanism for the formation of these guys. So initiation, right, initially to make the bromide radicals. And then this is currently not a stereocenter. But when I do my propagation step 1 for this primary, I create a radical on this methyl. So this methyl, it's no longer a methyl, actually. It has 2 hydrogens and a radical. And this is a methyl. So now this is a stereocenter. At that point, we made it a stereocenter. And since this is a stereocenter, you can consider like, oh, the dash back methyl or the wedge methyl, and they call them RNS. So I would say this is a higher priority. This would be the second highest priority. And then this one's missing a hydrogen, so it's lower. And then the lowest priority, H, is coming at you. So A, B, C, yeah, this is S, and that's R. Okay, and we'll make equal amounts of those, because the way you make equal amounts, you could think of it as like, if I showed this dashed before it reacted, it can come from either side. It's kind of complicated, actually, to verbalize why you'd make 50-50 on this one, but you make 50-50 on this one. And then after that, either one of these can react the same to give you your final products, and you'd expect to get equal amounts of both in propagation 2s. So Regio Isomer 3, same sort of thing. Start off with the tetrahedral carbon. Oh, and the radical carbons, they're trigonal planar. I mentioned that a while back, but it's really important to remember that they're trigonal planar. And this means that both sides of that trigonal planar radical has equal steric hindrance. So in the second step, when the BR2 comes in, it can come in from our side of the screen or the back side of the screen equally, because this thing's just, these 2 methyls are spinning around, and this one's hydrogens are spinning around, but it's symmetric around either side of this trigonal planar radical. And so when the bromine, the BR2 comes out the screen from my side, does it produce the wedge bromine or the dashed? What do you think? The wedge. Okay. And then what if the bromine, though, comes out the radical from behind the screen, behind what we're looking at, what's behind your computer screen, the wall there for me. So if it's coming from behind, that makes the dash. That makes sense, right? And since both sides of this trigonal planar radical look the same, they have the same steric hindrance, so we should expect the same amount of each. 50% of that, 50% of that. All right. So let's look at what we got. So we get a 50-50 yield of these 2 enantiomers, and we get a 50-50 yield of the other 2 enantiomers. Whereas the major product, the tertiary, has no stereochemistry, so I don't have to worry about enantiomers, diastereomers. And then Regio Isomer 4, no stereochemistry, don't have to worry about it. Okay, so now let's calculate yields with relative rates. So Regio Isomer 1, it comes from 6 hydrogens here, right? 6 hydrogens. And it has a reactivity of 1 for primary. And then I'm going to add that with all the other ones. So Regio Isomer 2, there comes from 1 hydrogen times 1700. Regio Isomer 3 comes from 2 hydrogens times 80. And then the final one, 4, is 3 hydrogens times 1. I could have put 3H times 1, but it's 3. So that means for Regio Isomer 1, I only get like 0.32% yield, not much. Regio Isomer 2, I get 91% yield, the major product, because it's just reacts so much faster. And then Regio Isomer 3 and 4. Okay, but this is just the Regio Isomers. I got to then add that into the Stereoisomers. So if it's 0.32% yield of this Regio Isomer, and there's 50-50 of the 2 enantiomers, I get like half of 0.32, only 0.16% yield of this enantiomer, 0.16 yield of this, 91. And then this 8.6 for the secondary, it's split into 4.3, 0.13. All right, so we got all our percent yields. And then let's look at the stereochemistry of this. So let's start off by talking about the reactants. The reactant has no stereochemistry to it. It's achiral. If you draw its mirror image, it's superimposable upon itself, so it's achiral. But this one will be chiral. These two will be chiral, and I'm going to make up some values. I didn't look these up. I just made them up. If this enantiomer is plus 11, then that one's minus 11. And if I have equal amounts of each, they'll just cancel each other out. They'll be a racemic pair. So these together, 0 rotation. This one's achiral. If you make a mirror image, it's superimposable on itself. These two, if this one's minus 17, that one's plus 17, together, they cancel each other out. This one's achiral. So what do we have all together? The whole mix is an achiral product mixture. So this goes back to my sentence I said earlier. If you have achiral reactants, you'll get achiral product mixtures. Kind of cool, huh? Yep, achiral reactants, achiral product mixtures. All right, so there's another example. Cyclo ones are a little easier. Ooh, this one's kind of tough though. So I'll let you click through that one. Let's do another one on my Jamboard. Let me see. Yeah, that one's a tough one. I have a bunch of examples here. You might want to skip this one unless you're brave. This is a good one. Okay. All right, let's do this example. It's hard to come up with a lot of examples for this and come up with them that aren't too crazy. And then I have to have an example, at least I really want an example that I'll put on the exam that's not exactly the same as the lecture example, but that's okay. Let's figure this out. I'm going to do a classic. I think I have another Jamboard of this. Oh, yeah, I do. Oh, I think I already have this one. I'm going to do it on the, I'm going to do, I think this is in chapter 5. Sorry, I'm all over the place here. Let's see. Oh yeah, here it is. That's okay. I'll make it a little different. I'll make it with no, I want to do it with bromine. Oh, you know what? I'll do yeah. What the heck? Sorry, my Jamboard got messed up. You know what I'm going to do? I'm going to do it as a 4-membered ring, so it'll be different than that animation. But that means I can't use the 4-membered ring for exam 3. Oh, well. Okay, we're going to go bromination here. You can also do chlorination and all that, but I like bromination because it is more specific. You know, you get the major, tertiary. All right, so I'm going to do a bromination of this one. How many Regio isomers will it have? Let's see, I'll start circling them. I'm going to go up here and I'm going to say these primaries here, the Regio isomer number 1. I'll call that number 1. And then this here, the tertiary, I'll call that one Regio isomer 2. Keep going. I got a yellow here. These are secondary. Those are equivalent, right? Regio isomers 3. And finally, this one here, another secondary. Did I call the secondary tertiary? I don't know if I misspoke. Secondary. Regio isomer 4. So I got 4 different Regio isomers. Oh, also, before I start drawing my product, is this molecule chiral or achiral? What do you guess? It's achiral. I know it because, like, if I really want to test it really quick, I can draw the mirror image, and this mirror image could be, you know, spun around and superimposed next door. So it's the same as its mirror image. It's achiral. Okay, and then the bromine, it's also achiral. So my products need to be all add up to achiral. All right, let me draw them up. I got 4 of them. I think it's best just to draw them up by initially drawing out the reactant without anything added to it. HBr. And then I'll add on my different products. So for Regio Isomer 1, it's got a bromine right here on the primary right there. There we go. Did that create any stereocenters for my molecule? No. So this, you might think maybe that's a stereocenter, but it's not because it's the same when we go around from either side. So no stereochemistry for this one. All right, Regio Isomer 2. It's going to put the tertiary bromide right there, right? Did that create any stereochemistry? Nope. Regio Isomer 3. Ooh, this one's this one's juicy. I'll put one like here, maybe. The secondary one, did that create any stereochemistry? It did. How many stereocenters did it create? One, two. That where the methyl comes off the ring. It wasn't a stereocenter before, but now it is. 2 stereocenters. So we're going to have how many maximum possible stereoisomers for that one? 4 max. We can get 4 different stereoisomers on that one. Okay, what about the final one? Oh, this one also is really tricky. Regio Isomer 4. Did that create any stereocenters? It didn't create any stereocenters, but it did create some stereochemistry about it. I'll get to it shortly. Maybe I should just do this one now. Let's just do this one now. So this one is tough. It actually creates 2 molecules still because this methyl can be wedged and the bromine then could also be wedged. Or you can have, say, that methyl wedged and the bromine dashed. This being the, this is the cis product. And this is the trans, trans product. It's easy to miss that one, huh? Because we don't see a stereocenter. You think, oh, it's just that one product. Oh, this one's got so many layers to it. So now what about these 2 molecules? How are they related? Are they the same molecular formula? Yes. Same connectivity? Yes. Different 3-dimensional arrangement in space? Uh-huh. So they are stereoisomers. Okay. Now, are they mirror images? No. So they're diastereomers. So an interesting case there. Also, what about optical rotation? Do they look chiral? They're not chiral. They're achiral. 0 degree rotation, 0 degree rotation. The reason why, well, I can just check it really quick. So like if I draw to look for chirality, you draw the mirror image and you see if they're superimposable. So can this be superimposable on its mirror image? For sure. I can just, rotate that around and it'll match up perfectly, right? So that one's not chiral, achiral. Then the other one, yeah, it'll rotate. They're both achiral. And then I've seen how many of you are asking. One of you so far asked, are they meso? Let's have a vote. Everybody vote. Are they meso? I see a yes for meso. I see cis is meso, trans is not. I want to say yes. They're not meso. This is a tough one. This would be like one of those super crazy hard multiple choice questions that everybody would miss. So why are they not meso? So not meso. Why? To be meso, you need to be achiral plus have a chiral stereoisomer. So these two guys, these are the only ways they can, these are the two, this is the complete set of stereoisomers here. Neither of them is chiral, so we won't technically call them meso. Crazy. So for instance, let me just show you a little aside here. So if I have like, say, this guy and this guy, this is a meso. It's got the plane of symmetry. The reason why it's meso, it's achiral, but it has a, it has to have a stereoisomer that is, this one is chiral. And it's a stereoisomer. They're diastereomers. This is achiral. So to be a meso, you got to be an achiral member of a set of isomers, one of which is chiral. Okay, that was a good little sidebar. Oh, let me clean this up a little bit. Okay, so back to our original problem. Let's see what time it is. Should we pause right here and then come back and finish it? What do you want to do? I think now's a good time to pause. We'll pause right here and then we'll finish this one up. And I want you to really understand this, because when you get it, it teaches you so much. You get better with the radical halogenations, your stereochem concepts all come together. And so on the exam 3, you will have a problem like this to do everything that we're doing. And it might seem like a lot initially, but as you work through a few of them, it clicks in, it all makes sense. So we started off with this methyl cyclobutane. And we saw that there'd be 1, 2, 3, 4 Regio isomers. We drew them up. Regio isomer 1, the primary. Regio isomer 2, the tertiary. 3 is the secondary. And 4 is another secondary. There we go. And we did look in detail at Regio isomer 4, which we saw had no stereocenters, but still had some stereochemistry. It had cis and trans stereochemistry. And these two stereoisomers are not mirror images, so they're diastereomers. And they really scream that they're meso because they have an internal plane of symmetry. They're achiral, so it seems like they're meso, but they're not technically meso because they do not have another stereoisomer that is chiral. They're just two achiral stereoisomers. Kind of a crazy one, huh? Okay, so now let's go back to these other ones. What should we do first? Let's do Regio Isomer percent yield first. Yeah, let's do that. Regio Isomer percent YIELE. Let's do that. Maybe I should write that out one. Okay, so I'll calculate one of them and then like fully, and then I'll kind of abbreviate the other ones. So let's work these out. The first one, regioisomer 1, how many hydrogens did it come from? How many hydrogens could have reacted on the reactant to make regioisomer 1? 3 hydrogens, right? So for that one, it's going to be 3 hydrogens times a reactivity of what? So remember, for brominations, primary, we have a rate of 1 relative to secondary is 80, and tertiary equals 1700. Okay, got it. For brominations. All right, there we go. We got 3 times 1 for that one. And then what about for the secondary? I mean, not, yeah, it's a tertiary one, but it's regioisomer 2. What about this guy? How many hydrogens reacted for this regioisomer 2? Yep, 1 hydrogen times a reactivity of what? 1700. Good. And then the regioisomer 3, which is secondary, how many hydrogens are we dealing with there? I started to write 2, but that's not right, huh? It's 4 hydrogens. Because there's 2 hydrogens here and 2 hydrogens here. 4 total times a reactivity of what? 80. Good. And then regioisomer 4, the secondary one, how many hydrogens were there to react? 2 times 80. Yep. Got it. Okay, let's work all these numbers out then. So we've got 3 total here. We'll have a ratio of 3 to 1700 to, what's that, 320? Is that right? 160, 160. I should be able to do this. Yeah, 320, right? Okay. And then this one's going to be 160, and that's it. So the total is, I could do this in my head, but I don't want to mess it up. So 1700 plus 3 plus 320 plus 160, 2183. Does that sound right? I'll check it. Minus 160 minus 320. Yeah, that looks good. So this one, the percent yield of regioisomer 1 is 3 over 2,183 times 100. And so let's do that. 3 divided by 2,183 times 100. 0.14% yield, like pretty much none of that, huh? Okay, so now for the other ones. For the tertiary, it's going to be 1,700. You can probably already see that's the major product, right? Divided by 2183. So it's 78% yield. And the secondary product, regioisomer 3, we got 320 divided by 2183. So that one's about 15%. But this is going to be, this 15% is going to be spread over possibly 4 different products because of Stereochem. And then Regio Isomer 4. It's 160. It's going to be half of 15%, huh? Yeah, it's going to be like 7.5%. Or I can do that one in my head, can't I? So I'm going to make sure I added these up right, because this should all add up to 100. Let's do it. 78 plus 15 plus 7.5. I got 100.5. It's just rounding. Looks good. Okay, so are we ready to go? This first one is easy. It's just, you know, one stereoisomer. There's no stereochem. It's just that molecule. We got 14%. Regio isomer 2 is easy. We're done. Regio isomer 3 is going to be a challenge. Now that one, we're going to have possibly 4 different stereoisomers, huh? It's going to be 2 to the 2, 4 max stereoisomers. Let's try to draw those out and figure out what's going on, see if there's any duplicates. So we can go wedge, wedge. How many of you are like pleasantly enjoying this, like thinking, oh, wow, I thought the Stereochem, how did it relate to the radical halogenations from before, bond line structures from before? It's all coming together. Okay, we got them all right. So are any of these duplicates? What's your guess? Do you think we got any duplicates in here? Nope, there are no duplicates. I'll calculate RNSs. A, B, C, this one's S. So that's, let me double check. A, B, C. Yeah, that's counterclockwise. And then I should do that in yellow, maybe. Let's keep consistent with the colors. So that means this is S, that's R, and that's R. Okay. And then the next one, this guy, it's going to be A, B, C, R. R, R, S, S. Okay, so I've got, these are definitely different, the R, R, S, S, but these ones, they might be the same, R, S, S, R. But in order to match up this R with that R, I have to flip this over to see if they superimpose. They don't, because the bromine will be on the methyl and the methyl will be on the bromine. It won't work out. So no duplicates. While we're at it, we can say how they're all related. Why not? Huh? Let's go. What's this one? This one is, how are these two related? Enantiomers or diastereomers? Are they mirror images? Enantiomers. What about these two? Do they look like mirror images? Yeah, enantiomers. These two. Mirror images? No way. Diastereomers. Same here, not mirror image, diastereomers. And then diagonally, diastereomers, diagonally, diastereomers. Okay, got all our relations made up. So, but what I need to know is, do I make the exact same amount of like all of them? Do I make like, there's a total of 15% of these 4 molecules, but is it going to be like, how would I just 7.5? 3 3¾ 3 3/4 3 3/4 3 3/4, or will there be a differing amount of each? How can we figure out, do you think? Or how can we make a guess as to whether we make the equal amount of both, of all 4? The key is, you're right, Ryan. And then Ryan's saying the trans products will have more of those relative to their cis. And he is correct. How did you know that, Ryan? steric hindrance, and then steric hindrance related to the mechanism. That's the key. So for these, you have to look at the mechanism. So let's do this. I'm kind of running out of all my room here. I'm gonna do it. Try to shrink this guy down over here. Can it shrink? Oh, it can. Oh, no, it can't. Yeah, I'll squeeze it in here. So we need to look at the mechanism. Mechanism is the key. I don't know why that got ugly. All right. Oh my goodness. Sometimes, man, you just don't have enough board. So here's the mechanism real quick. You don't have to draw out the whole mechanism. There's only key steps that you need to draw, but just as a quick review, I'll show you. Initially, we start off with, initiation. Okay, and then we react at that particular carbon there. So we have, say, initially no stereochemistry here. We have 2 hydrogens here, and our bromine will come along and take off one of them. Can you meet me halfway? So we go from having a bromine radical to a carbon radical. And this carbon radical, it makes HBr as well. This carbon radical, it's interesting in that now that radical is trigonal planar. Originally, the carbon was tetrahedral, right? After it loses a hydrogen, it goes trigonal planar. And we create a stereocenter right here. Initially, it was no stereocenter right there. Okay, and this, since it's a stereocenter, I can draw it up as two enantiomers. So I can have like the wedged out version and the dashed out version. And I'll have an equal amount of those. The reason why I'll have an equal amount of those is this non-stereocenter methyl, it could have been wedged out, and that means the bromine would want to come from the opposite side of it and get the hydrogen that's dashed. If this is wedged, it will more often want to get dashed, but then this can just as equally be dashed, and then it'll want to get the wedge. So it'll be a 50-50 mixture of these two. At this point, equal mixture of both, right? All right, and then when our bromine comes in for the second step, or the third step, propagation step 2 though. It's gonna go boop. Can you meet me halfway? And it will give me 2 products for this one. It'll give me a bromine that's dashed or a bromine that's wedged. And of course, the bromine radical. Okay, so which one of these 2 do you think is made more, or do you think they're made equally? Do you think Ryan's saying this trans one is made more than the cis one. Why do you think that, Ryan? And Santos agrees. Why do you think so? Yeah, steric hindrance. So this, when the BR2 comes in, it can come in from our side of the screen. And if it does, it has to avoid this methyl. But if instead it comes from the back side of the screen, there's just a little hydrogen in the way. Less steric hindrance for that backside attack. So let's say that this produces like 75% of that one and only 25% of that one. I'm just making those numbers up. I'm saying that, you know, there's going to be more of the trans, less of the cis due to steric hindrance. Get myself some more room here. Okay, same thing here. I won't draw out the mechanism this time, but I'll just put BR2. So we're going to get, again, two products. One of them with the bromine wedged here, and one of them with it dashed. All right, we got them. So do you think we're going to make more of one and less of the other? Wait, what'd I do? I made a typo there, huh? I need a dash, dash, dash here. I didn't make a typo. I made a digital pencil O. It was with the Apple Pencil. Okay, so am I going to make more of one? Sure am. I'm going to make more of the trans, say like 75%, because it's going to be less steric hindrance to come from this side of the screen to make a wedged bromine because the methyl's pointing away. And then I'll make like 25% of that one. Okay, so let's put it all together. Are you ready for this? Let's go back to this guy and transfer our information. I said we'd make about 25% of that wedge, and like 25% of the dash, the cis ones, 75% of the trans, 75% of the trans. There we go. Okay. So what about chirality? Let's say I produced, let's say this particular molecule, the 25% upper left one, let's say it has a rotation of like -9 degrees. Can you tell me anything about other rotations of these set of stereoisomers? Yeah, since that one's -9, its enantiomer is +9. So this one is +9 degrees. Good. And then since I know this right here is -9, does it tell me what this one will be, the diastereomer? No, I'll have to make up a number for that. Let's say that one is +17 degrees. If that's +17, then what else do I know? This is -17, huh? So the cool thing about this is that this enantiomer +17, there's 75% of it. This enantiomer -17, there's 75% of it. These two make a racemic mixture that cancels out. So these two cancel each other out, they're achiral together. And these two enantiomers are also achiral together. And there's an equal amount of them, 25, 25. So working through all this, I started off by telling you, if you have an achiral reactant, which we have up here, your product mixture will be achiral. Now, is this true? Let's add on the rest of the rotations to make sure. This first one up here, this Regio Isomer 1, it is achiral. It has no stereocenters, and it's same as its mirror image. Regio Isomer 2 is also achiral. It has no stereocenters, and it's the same as its mirror image. Regio isomer 3 is a tricky one. All of its stereoisomers that are produced all together, these all add up to 0 degrees rotation. And stereoisomer 4, we wound up doing that one first. They're both achiral. So all together, we went from achiral reactant to achiral product mixture. Who likes it? Intellectually pleasing, right? That's right. If they didn't all cancel out, then my statement of achiral reactants becoming achiral products would be wrong. I like that. I like how you go through all that and you're like, yeah, it worked. Makes sense. All right, and then the last thing is, yeah, we can do examples where they don't cancel out. Actually, I'll show you shortly. But before I do an example where they don't cancel out, where, for example, if you start with chiral reactant, then you'll get chiral product mixtures, possibly, usually. Okay, so now, before I do that though, let me do like a full summary of all this on the next panel to make sure it's making sense. So full summary, we started with methyl cyclobutane. We brominated. We got this Regio isomer. We got the tertiary, this is the major one, right? Then we got all kinds of secondaries. You know what, I should keep those. I should switch those. I think it's a little more clear. Okay, and then we got these ones. All right, percent yields. Let's see what we got. We got 0.1478, 0.14% yield, 78%. What did I do? Sorry, I'm zoomed in and confused. Zero 0.1. Ugh. 78% yield. This is the major product. And then these four, they all added up to 15% yield, right? But I'm going to figure out 25% of 15. Wait. These are relative to each other. So like half and half. Ugh. So let me do the math on this. So it's going to be 15% yield. Has to be divided into quarters. No. Eighths. There's a little bit of math here. Sorry, I didn't mean to make it this confusing. So it's like 1.875%. That's an eighth, which is a quarter. So So this one will be 1.875%. This one will be 1.875%, I think. Let me double check this. So then if I times that by 3, 5.625%. Let's see.
You're still on the other screen.
Thank you. So I'm getting these percent yields to add up to 15. So these need to add up to 15. Do they look like they add up to 15? Yeah, I think so. And they're 25, 75 relative to each other. Or 75, 25. Double check before I walk away from this one. Okay, let's go. 1.875 divided by 5.625 equals that. That's third. Let me make sure I do this. 7.5. Wait, 7.5 divided by 4. That's what I need to do. Yeah. Okay. Oh, wait, no, that's a quarter. Sorry. 7.5. That's good. Oh, it's the total. That was my problem. 1.875 divided by. Yes. Okay. I did the math right. Okay. And then these two. Oh, shoot. I didn't work those ones out. Do I get an equal amount of those two? And then James, you're asking if something was meso, but there is no meso in this one. And now, yeah, Ryan's saying I'm getting more trans. More of this trans. Let's look at the mechanism and see. Mechanism is key, like I've been saying. So what this comes from, this is our most full Jamboard slide ever, huh? What this comes from is initially you have, imagine if you have like a wedge, this methyl's wedged, and you made this radical here, and then the bromine's coming in to react with it. Can you meet me halfway? Which side is easier to attack? The side opposite the methyl wedged out, or the same side as the methyl wedged out? I'm saying it's easier to attack this side. So I'm going to go like 80%, 20%, say. More trans again. Less steric engines on that side. Okay, so what was my percent yield of that one? 7.5%. And I'm going to say it's 80-20, so 7.5 times 0.8. I get 6% of the trans and 1.5% of the cis. 1.5%. Yes. Whew, I got through those yields. So if I did those yields right, they should all add up to 100. And I think they do. That's 7.5. Yeah, it looks good. And then lastly, I'll add on the chirality information to summarize this one, and then we'll call it quits. So 0 degrees rotation for the reactants, 0 degrees for the bromine, 0
Hey,
degrees
Mark.
for this one. Yeah. Oh, did I not switch pages? Sorry.
Yeah.
Thanks
Yeah.
so much. 0, 0, 0. This one, the trans methyl up, what did I predict it as? I just said it was plus 17. Huh? So I said this one was plus 17 degrees. And then I said the other one was the enantiomer would be minus 17 degrees. And there's an equal amount of both made. And then the cis ones, I went dash dash was plus 9. Plus 9 degree rotation and minus 9 degree rotation. There we go. So those all cancel. This one's 0 degrees. This one's 0 degrees. We're done. Woo. We did good. We finished chapter 5. That was a long one, huh? I forgot. I was going to show you at the end of chapter 5. There's some slides here talking about, and this is in the PowerPoint slides, about the why you get more stereochondrites, less stereochondrites. I'm not in love with these ones, but they're still there if you want to look at them. But here I have one. This is what Ryan was asking about. I have a molecule that starts off chiral, huh? I'll just click through this really quick. I'll let you click through it later. So you start off with this guy's got a stereocenter. It's chiral. And I circle all my Regio Isomers, draw them all out. No stereocenter, 1 stereocenter, 2, blah, blah, blah. Check the mech. And these ones, you don't get an even mixture.